Good afternoon, everyone. My name is James Collins. I'm a geospatial analyst with the City of Austin Watershed Protection Department, where I use GIS every day to administer Austin's stormwater utility fee. Welcome to Show Me the Edits, a case study in using Feature Manipulation Engine, aka FME, data translation platform, and the open source Leaflet JavaScript library to deliver interactive, ad hoc previews of proposed GIS data edits to customers and stakeholders. Here's a quick roadmap for the next 15 minutes. We'll start by covering the background of this use case and what our business process was lacking. I'll then describe the parameters of our problem and what our solution needed to address. Then I'll present the novel solution we've developed for our group using FME and Leaflet, and I'll also jump into FME and the new application itself for a demonstration. Finally, I'll briefly cover the abstract case conditions for which this approach may be suitable before taking any questions after the pre-recorded session. So starting with the background of our case study. My team of GIS analysts and myself administer the City of Austin drainage charge. This is a utility customer fee that funds essential stormwater drainage infrastructure and services across Austin. The drainage charge is calculated based on each individual property's parcel and impervious cover. For example, the image on this slide shows the parcel boundary and impervious cover features for our office building. Utility customers that pay a drainage charge can dispute their rate in the impervious cover data on file. And these data are stored as a feature class in an ArcSDE Oracle geodatabase. During disputes and corrections, edits are made in versions and then committed to the geodatabase. The dispute and correction process is what we're focused on in this case study. To sketch this out more clearly, here's the steps we take when performing GIS edits. First, the customer calls in to initiate a dispute. After reviewing the property and any supplemental documentation, we make edits in a version. We then send a preview or summary of the edits to the customer for their approval. The customer reviews the preview and either gives additional feedback, or they approve of the edits, at which point they're committed to the geodatabase. The shortcoming of our process has been generating a preview of the edits in an uncommitted version. Our existing process has been to either take screenshots of the GIS application showing the edits, or for more complicated edits, export a static PDF. Both approaches have clear shortcomings. It's difficult to make a standardized static product that works for all situations, and therefore it can be time-consuming to create, describe, and descriptively map these edits. Screenshots and PDFs both require some amount of written interpretation for the customer to understand the graphic. And neither screenshots nor PDFs are easily made interactive, with functionality like panning, zooming, and measuring features. These limitations became the parameters for a possible solution. We set out to create a preview of edits that is standardized and provides the same level of service to each customer, that's quick for the GIS editor to make, that is intuitive and self-explanatory for the end user, that allows the end user to interact with and discover new things from the data, and that's made for a single user, not the public, because the content of these previews show information related to a single customer's dispute. So with those parameters, we developed a novel solution that uses FME to bring features out of the versioned ArcSDE environment and into a lightweight format that can be rendered on the web using Leaflet and JavaScript. The process starts by the GIS editor saving edits to a version in the geodatabase. Then the editor supplies a few parameters to a web-accessible FME server workspace that queries, analyzes, and translates the edited features. FME then outputs these features as JavaScript object notation, or JSON, and associated aerial imagery as a web-ready PNG. Finally, a link is supplied to the customer. The link includes a unique identifier that loads the FME-generated data into the web map. Here's a more detailed diagram of the process, but I really want to focus on the FME server application, as this is really the key component of the process. As a data translation and transformation platform, FME is well suited for analyzing the differences between the production and edited GIS data. In our process, the FME workspace adds descriptive attributes to the queried GIS data, such as edit type, feature filtering attributes, and the calculated utility fee rate. FME works great at capturing a snapshot of the edits in an uncommitted version and essentially exporting this snapshot into a usable format, like JSON, that we can share with the customer. So after walking through the background of the case and outlining our solution, I now want to demonstrate this process with some sample edits. I want to start by showing the FME workspace that queries, analyzes, and translates the ArcSDE features. It's a rather complicated workspace, so I'm just going to walk through the broad steps that we take. I want to start by showing the parameters that the GIS editor supplies to the workspace. These include a job owner name and job number that's used to find the version in the geodatabase, as well as a comma-separated list of the parcel IDs that we want to map. There's also some additional parameters that are used to change how the data is displayed in the final web map. So when the workspace is run, we start by querying the database for the impervious cover and parcel features in both the production dataset and in the version. We also query an address point layer to find the best address with which to label the parcels. Now, there's both processes for analyzing the impervious cover data as well as the parcel. They're pretty similar, so I'm just going to walk through one of them. So we start by doing some geographic transformations or geometric transformations, including reprojecting and extracting the geometry to a JSON format. We then add some symbology attributes and other attributes that are used in the display in Leaflet. This merger compares the edited and original features by a unique ID to determine the type of edit that was performed. And then based on the type of edit, whether it was a create, delete, or update, there's different symbology attributes and other feature details that are added. Finally, after some formatting of attributes and sorting, we're ready to pass those features onto a transformer that combines them into a single JSON output. Now, jumping over to this process that is analyzing and exporting a clip of aerial imagery. So we start by dissolving and aggregating all of the features that are mapped in the preview to create an area of interest. Then query an imagery mosaic data set by the area of interest, and we clip the returned imagery by the area of interest. We then reproject that and perform some band operations to convert the aerial imagery raster into an RGB format that we can export to a web-ready PNG. We also extract some georeferencing information that's used in the display of the imagery. Next, we generate a unique identifier string that's used to label and locate the preview data. This includes a timestamp, the supplied job number, and a hash generated from the data itself that ensures that the ID is unique. Second to last, we write out the data, including the JSON and the PNG of the aerial imagery. And finally, we send an email notification to the editor that includes a report of any errors that were found, as well as a link to access the preview that they could forward to the customer. Now that we've looked at the FME workspace that queries and analyzes the data, I just want to briefly show how this is implemented in an FME server as an FME server app. So this is a web accessible interface that is actually used by the GIS editors. And again, we have the same parameters that we saw, essentially the job owner and job number to find the version, and again, the ID numbers of the parcels we want to map. And so an editor would input those parameters here, click OK, and that would initiate a process. It would initiate that workspace on the back end, query the data, and upload the results to the web server that's hosting the Leaflet Web Map. Okay, and now for the big reveal. Let's take a look at the Leaflet Web Map that visualizes the data output from the FME workspace. So here's the web map, which we've titled the Drainage Charge Property Preview, populated with some sample edits. I'll scroll through the informational sidebar, which includes the tabular data and attributes that we want to share with the customer. In this introductory section, the application includes informational text and instructions with every edit preview. This standardizes the service provided to customers and helps make the tool more intuitive. The descriptive text is included with the web page that loads and renders the data, so it doesn't need to be rewritten or regenerated for each customer. The next section summarizes the parcel level data and what's probably most important to the customer, how their utility rate has changed. The customer can intuitively hover over attribute names to get more details and better understand the data. The customer can also click on the parcel card to highlight the parcel on the map, and vice versa. This is useful when multiple parcels are involved in a single dispute. The last section details the impervious cover features. The rendering web page generates a paginated list of impervious cover features from the JSON data file, with the edited features sorted to the top by default. For larger properties with lots of features, like this one, the customer can get more granular and filter the features by various characteristics. Like the parcel information card, the customer can click on an impervious cover feature to get more details, including a summary of how the attributes were edited. Clicking the cards also highlights the map feature, and vice versa. Once again, tooltips give more contextual information to the data. Now to focus on the map itself. By displaying the data in an interactive format that's increasingly familiar to customers, the web map dramatically improves our ability to communicate GIS edits. Customers are able to pan, zoom, and interact with features in the map. The customer can also modify the map view, such as to only see the currently billing data or just the imagery itself. Because Leaflet is open source, many contributors have extended its functionality. For example, an open source plugin provides a configurable measurement feature. Finally, an automatically generated legend only includes symbology types that are displayed in the current preview, so extraneous information is hidden to declutter the application by default. And one final thing, the web map is made to play nicely with phones and small screens. The interface is automatically simplified, but the user can still interact with both the map and the tabular data in the preview. As customers increasingly use phones and other small devices as a primary computer, having a way to communicate spatial data that takes advantage of the interactive nature of small devices is important. So, to recap, using FME and Leaflet to display GIS edits is standardized. It provides a single web app that can be configured to display data the same way with the same informational text and features. It's quick to make. The FME workspace automates the analysis of edits, and Leaflet renders the output of the FME workspace. It's intuitive. The application can be configured to present the appropriate level of data, interpretation, and guidance to each user. It's interactive. The user can manipulate map data and drill down into more details. And it's single user. The FME workspace creates an output that is specific to the user, and only those provided with the unique access link can see the preview. To wrap up, I want to move from our specific use case to the abstract case by pointing out some general conditions for which this FME and Leaflet approach may be suitable. First, if there are thematic GIS layers that are subject to some external user, customer, or stakeholder input. If users have varying levels of understanding and familiarity with the GIS data, and if a guided or interpretive environment is best for them to interact with the data. If users may request views of the data. This could be many iterative views as the data is modified in response to feedback. Finally, if the data views need not be permanent, but serve a limited and ad hoc purpose. Other potential applications for this method may be in site engineering, architecture, or municipal programs, or other situations where GIS data needs to be communicated to specific members of the general public. That concludes my case study. I hope this was a useful demonstration of using FME as a glue between enterprise GIS and open source custom web maps to share small, uncommitted views of GIS data. Please feel free to contact me for more information or resources from the process shown here. I'd also love to connect via email or LinkedIn and meet y'all and learn more about your work. Thank you.